Hi guys, my name is Ian and I'm back with something else to do with Arduinos and electronics. It's going to be quite different from what I've done before. I'm looking at things like this. This is a lead acid battery. Not one out of a car, it's one out of a UPS. Recently one of my UPSs started beeping, incessantly beeping, and it needed a new battery. Replaced the battery. I've got a pile of these batteries. I'm wondering, well, are they faulty? How do I know? So you can charge them with an ordinary car battery charger. In fact, of the several that I did have that were allegedly faulty from the UPS, this thing condemned 3 of them as well, but it didn't condemn one of them. So I have got some code and some hardware that is comparing a known good one with this one that the UPS doesn't like, but the battery charger said was alright. So let's have a look at some hardware and software. So if I show you this is the schematic of what I have built. Alright, so what you can see, you can obviously see my mess of wires, and you can see the nice fritzing pretty diagram of it. We're measuring 12 volt batteries. Obviously we can't put 12 volts straight into an Arduino, well, at least only once. So we have to divide the voltage down. So that's what this piece is. This is a voltage divider. These are 100k resistors, one of them and 2 of them in parallel. It's given me basically a 1/3, 2/3 voltage divider, so that's good for about 15 volts of battery voltage, and it'll give me no more than 5 volts to the Arduino, and then I can scale it up, not a problem. Other bits in the circuit, I've got some LEDs to tell me that they're on, and as you can see I have an LCD screen. Now the LCD screen also has a control, and if I lean over and touch the control wire, you will see the screen light up, and you might even be able to read a bit of that until the camera decides it can't focus on something so bright. But anyway, that's what we've built. And what am I seeing? Well, I'm seeing that I can see the voltage. I'll show you what it looks like if we zoom in on the hardware a bit closer, so you can see things. The screen, the LCD screen in the top right corner is a picture of what it looked like the other day. What you can see in the main camera is what I'm looking at now. So you can see I'm measuring. One battery is already down to 4.33 volts, and the other one is still 12.5. Now, what have I learnt about 12 volt lead acid batteries? Well, when they're fully charged, they're actually a little bit over 13 volts, and the charge drops quite slowly under very little load. Now the battery, it's measuring 12.5. It's been running for a week, powering this one of these LEDs. The other battery, the one that the UPS doesn't like but the battery charger does like, well, when it was fully charged it was a little over 11 volts, and within 2 days it had dropped to 6, and it's been running for another few days and it's already down to 4.5. So clearly the battery 1 is not good. Battery 2, which is my known good, is good. So let's look at some code. So first thing we have to think about with the code is there's an LCD screen. This particular LCD screen is on the I2C bus, which is why it was only connected with 4 wires. You've got the data clock, and then you've got plus and 5 volts. 5 volts and ground, sorry. An ordinary LCD has loads and loads of wires, and to be honest it was too much wiring for me to be bothered with. So you need an LCD library, liquid crystal library, that supports the I2C bus. Now there's lots of them available. I picked this one. So this one that you can see is it's the HD44780 by Bill Perry, and it's actually got great documentation, fully open sourced. He's done a great job, and there's loads in there. In fact, there's for more screens than even I've got. I had to pick up a certain part of his library to use, but it was all very, very easy to do. Lots of examples in his code and on his GitHub. The link is in this code if you wanted to go and see it, but you can install the library through the library manager with the Arduino. So let's have a look at some of this code. So these are my libraries. Obviously we're using I2C, so we need the wire library, and then these are the libraries to drive HD44780, and then this is driving the HD44780 through what they call an I2C backpack or expander board. It's a little board that is actually stuck onto the back of the LCD, and that's what gives it the I2C bus. I then have some defines. The code I've written can work for up to 4 batteries. I had spare wires, why not? This bit here, this is the AV RF monitor. I'll get to what that's about in a minute. That's a little bit of cleverness that I came up with to cope with a problem that I had with this Arduino and this circuit and this connectivity. Then I've got a control wire for the backlight of the LCD. That's quite simple. You ground it, turns it off. You pull out the ground, turns it on. There's a bit of code that watches digital pin 2 and calls the appropriate function for to turn the backlight on and off. Then we've got a bit of code, a few defines for the reading the analogs, and then this is the interesting bit, how I am reading the analogs and how I'm calibrating what I read. Okay, then we've got a bit for the voltage divider. Mine is 150, so it's 100k and 50k, which is basically a factor of 3. And then I've got some stuff for the LCD, and then we're into my usual stuff where I have a millis loop with different jobs on different cycles. So setup, we set up the pin modes, etc. We want some serial because we're outputting the voltages on the serial. The reason for that is we can capture that data and we can graph it, and I want to be able to graph this voltage over a number of days or weeks and see what happens with my good battery versus my not good battery. I know it's not good, but I didn't think it was quite as bad as it turned out to be, but there you go. Anyway, this is the bit where we are calibrating. I'll explain that in a bit more. We only run the calibration once. Every time we start up the Arduino, it calibrates what the voltage is it's reading in through the analog inputs. I will explain that in a bit. Let's run through the rest of the code first. We've got the usual loop. We read the batteries, we output the data. We've got a flashing light for the heartbeat. I like to know my Arduino's doing something and hasn't crashed. Sorry, that's that there. That's the backlight control for reading in digital too. And then we've got the heartbeat. We have a wee bit of ADC reading code here. This is interesting stuff. What you'll notice is that there's an initial dummy read. Turns out that the Arduino, this is a nano, so it's got 8 analog inputs. It might have 8 inputs, but it only has actually 1 analog to digital converter, and it muxes them. So when you select pin 0, it moves its ADC over to pin 0, and then when you select pin 1, it moves the ADC to pin 1. Now what this is about, this dummy read, is about basically forcing it to move to the new pin. It takes a time to settle, and there might be residual charge from the last pin, so this dummy read is to get rid of that. So we do a dummy read to move the ADC mux, and then we wait for a bit for it to discharge, and then what we're doing is we're reading what we want, and we read it a number of times. And there's a wee bit of adding 0.5 here. If you look at one of the links to the how to measure properly with an ADC, you'll understand this is about averaging the quantization noise. But we've read it in, say, in my case it's 8 times, and then we push back the average. That's all it does. Then we've got a bit of code for printing the voltages to the serial. This is for the logging and the graphing. Then we also print a setup on the LCD screen, so the stuff that doesn't change. And then period every time through the job number 2, we update on the LCD how long we've been running, which is basically how many times we have sampled the voltages. It's the sampling at the minute, it's once every 5 minutes, so you can work out how long the thing has been running, and that's to give me an idea how long my test has been running. The minute it says it's been running for 8 hours and 45 minutes. Then we've got LCD, print the voltages out, and this is how to show an individual voltage. So this is called by this one. All these numbers is printing different numbers at different cursor locations on the LCD screen. The LCD screen's a 20 character by 4 line. So you've got column and row, column and row. So that's printing the B1 and the B2, and then the third row for the B3 and B4. Now, back to this calibration thing we're talking about, where it starts here. Now, what I found was, when you're doing an analog to reading, you basically get a number in, say 750. It's a number between 0 and 1023, which is the maximum for a 10-bit ADC. So you've just read in 750. Now, what does that mean? Well, it means a voltage between 0 and 5, you would think. Well, it would mean a voltage between 0 and 5 if indeed the 5 volts into your Arduino was 5 volts. In my case, it turned out when I was running it through one port on my computer, the 5 volts was actually 4.69. I then moved myself onto a powered USB hub, and I discovered that my 5 volts is actually 4.5 volts. It's not 5. Now, obviously, if 1023 doesn't mean 5 volts, it means whatever your voltage is. You need to know what that is, but how do you measure it? So what I came up with was, despite the fluctuation in all my 5 volts in 4.5, 4.6, 4.7, the 3.3 volts out of the Arduino was pretty much rock solid 3.3 volts. Okay, it might have been 3.29 sometimes, but it was far more stable than the 5 volts that I was feeding from my USB. So what I have done is I take the 3.3 into analog input number 7, and whatever it is read as, it might be 750, it might be 650, who knows, whatever that number is, I know that means 3.3 volts, and I can scale and factor the rest of it, everything else I read, on the basis of what I know what 3.3 volts is. I can work out what the range, what the actual 5 volts going in to my Arduino is, and I work it out, and then I use that to correct all the readings I get, and lo and behold, it works. Or at least it worked for me. So what I found was what it's telling me on the screen. If we go back to that, I'll show you, assuming it is still gonna read it for me. Oh yes, it is. When I measure the voltage on the top of the battery, and if I go through what we've got here, so that's the LCD screen, that's the Arduino that we're using at the minute, that's my Nano. These are the 2 LEDs that tell me whether the battery's on or off. Top one is battery 1, bottom one's battery 2. Then this is the voltage divider business. This other Arduino and stuff, just ignore that, that's from another project where I was upgrading my Nano bootloaders, and it's still on the board. Battery, down here, you can see the terminals just at the bottom of the screen here. Battery 1, battery 2. Now, you can see that battery 1 at the minute is reading 4.33, and lo and behold, if I put my multimeter on that, it is 4.33. It's accurate. The 12 volts isn't so accurate. It might be reading, and what's it reading? 12.49 at the minute. When I put the meter on, it's maybe 12.53, well within what I count as acceptable. Whereas if I was just assuming my 5 volts was 5 volts, my figures were nowhere near right. So anyway, that's what we've got, and it works. So what's the most important thing I think in this project? What did I have most fun with? Well, the LCD was fun to play with. Using this library, it was actually made what could be quite complicated and nasty. Some of the code behind the LCD library is actually quite in depth. I've read the data sheet for it. I was thankful I got Bill's library. But the best fun I had was working out this calibration. The calibration factor, that was the most fun, because whenever you're doing an ADC reading, you've got an equation where you're trying to work out what the voltage is you've just measured, and you've got 2 knowns and 1 unknown. So the voltage you're trying to measure is the unknown. What you've just measured is its ADC value, and the other thing that's the known is your power supply, the 5 volts. But when you turn that all around to calibrate, you end up with, you've got 3.3 volts. What you've just measured, you know that. The other thing you know is the ADC value for that, and the unknown then is the 5 volt, whatever it turns out to be. So you've just turned the equation round, and that's all this does. All this code does is turn that equation round. So that was definitely the most fun, and it definitely felt a good success when I got it to work. I think that's about it. All the code and the diagram and the pictures will all be up on GitHub, link at the bottom. And if you like this, give me a like, and until the next time, goodbye.